If we look at number 11 as an example, who had number 11? Okay, number 11. All right, number 11 is asking what is the KSP for silver bromide if the molar solubility is 8.8 times 10 to the negative 7th moles per liter. Now, this problem doesn't give you a lot of information, but it says it's a KSP problem. And a KSP problem is always when you have a solid dissolving at equilibrium with its ions. So this is a special equilibrium. In this equilibrium, now we just write our K expression. K equals our silver times our bromide because they're aqueous. But do we include the silver bromide solid? Nope, we don't include the silver bromide, so that is our KSP setup. Now, once we have our KSP setup, we look at the problem. The information we're given is moles per liter, which is equal to molarity. Molarity is in concentration units. So we're given the concentration in this problem. Now, if the concentration of this was S, the concentration of this would also be S. So these two are always going to equal the concentration value because it's a 1-to-1 ratio. So the concentration of the silver is equal to 8.8 times 10 to the negative 7th molarity. And the concentration of the bromine is exactly the same in this case because it's a solid dissociating into those ions. So you multiply these two together and that will give you your KSP value. Does that make more sense, Amanda? This is what we just talked about earlier today. So if you couldn't do that before, that's a special K problem. KSP also stands for special K, solubility product. Uh, 12 and 13 are also KSP problems. No, 12 is, I'm sorry. So the problem with 12, it's a little bit trickier, but I will show you this. However, I want to give the warning. You will not have to do this on the test. You will not have to do this on the test. That's the warning. So if you don't want to watch, that's totally fine. I understand. Number 12, you will not have to do on the test. And this is what we just learned today. Now, number 12 is a little tricky because the formula is different. HgI2 breaks up into Hg and I2. What would be the K expression for this one? If this is solid and these are both aqueous, K equals what? So we do need to be able to do this for the test. This part of the problem. You're given an equation. What's the equilibrium expression for that equation? What is written first? Hg plus 2 times what? I. And what power is the I2? Squared. Now, this here would be how to do the equilibrium. If you were told the concentrations of this or the concentration of this, you could do the problem. Okay. Now, in this particular problem, it does give you the solubility. So it gives you the S. The problem is, if this is S, this one has what ratio? What's the ratio between the H, G, and the I? 1:2. So if this one is S, what's this one have to be? 2S. So then you just plug in the value for S, which is 2.2 times 10 to the negative 10th. That's for this one. And then you do 2 times the 2.2 times 10 to the negative 10th. Squared. It must still be squared, and that will equal your KSP value. It's a little more challenging if you had to do this backwards, but it would still be the same setup. The same setup, you would just have to solve your equation differently. Does that make some sense, Amanda? That was given in the problem. It was the moles per liter, which I know is molarity. In the problem I did, that was where I got it from. It might not be the same on yours. Then you use that value in here. It has OH parentheses 2. Yeah, the OH ion would be the one that has double the moles. Yeah. Is your problem with calcium hydroxide or? Yeah, so it's a similar setup. It'll be a similar ratio, it'll just have different numbers and same 1-to-2 ratio. Yep.
On the bottom, is that 2 times 2 times 2 times 10 to the negative 10?
2 times 2.2. It's double 2.2 times 10 to the negative 10. Yeah, sorry about that. It does look all the same to me. Your version's different? Yep. So whatever your version says, you do that steps based on the reaction you have.
4.14 times 2 times 4.14.
I think that would work for nickel hydroxide. You draw out the equation for it, and it should be similar. All right, the next questions we have are on fire. Not literally. On fire section for period 2, let's look at question 40. Let's see if I can get to question 40 here. Is that the one with the sodium hydroxide being dissolved in a solution? All right, so if I can call this up, I will see it. So on question 40, you have a certain amount of sodium hydroxide, and it's dissolved in a certain amount of water. So let's view someone's quest to see number 40. All right, number 40 is asking for the temperature change. So it wants the delta T when 24.6 grams of sodium hydroxide with a negative 44.5 kilojoules per mole enthalpy of solution. So this is the delta H when it is dissolved in a solution. It's dissolved in 160 grams of water. And it says that the specific heat capacity of the solution is equal to 4.18 joules per grams Kelvin. Now, the good thing about Kelvin and Celsius is even though they have a different scale, 1 Kelvin is equal to 1 degree Celsius. So you can change this to a degree Celsius unit here, first of all. The next thing is you've got 24.6 grams of NaOH. So you have to convert the grams to moles of NaOH. In NaOH, the molar mass is 40 grams per 1 mole. So you cross multiply this, 24.6 divided by 40. This gives us 0.615 moles of NaOH. Then you use the heat for dissolving this to find the kilojoules produced. So if you had 1 mole, it would produce 44.5 kilojoules. 0.615 times 44.5 And this equals 27.3675 kilojoules. Now, this is the amount of heat that is given off by the solution, given off by the solid. So that means it's being absorbed by the solution. So positive 27.3675. If you multiply this by 1,000, 1, 2, 3 places over, this gives you the amount of joules that are going into the solution. Once you have the joules that go into solution, you can use your mass times specific heat capacity times change in temperature. The tricky thing about the mass is this is 24.6, this is 160, so you have to add them together because it's for the solution. So 184.6 grams is for the entire solution. This is 4.18 joules per gram degree Celsius, and the delta T is what you don't know. So then you just solve for the delta T, divide by 184.6, divide by 4.184, and this gives you 35.4672 degrees Celsius. So that is how to go about a problem like that. Yes, sir?
So, will we be given any constants or like specific heat and stuff like that? Or
You'll be given any constants you need, yes.
Okay.
Only thing you won't be given is specific heat capacity of water is 1, and in joules it's 4.18 joules per gram degree Celsius. So that's the only conversion factor you would need, as long as you know water is 1. Yeah? Whenever it says enthalpy, that is equivalent to heat of. So it says enthalpy of fusion, that means it's heat of fusion. Enthalpy is just for a particular temperature and pressure. Heat of reaction is only when it's at 25 degrees Celsius and 1 atmosphere. So if you have enthalpy, it doesn't say anything about the temperature or pressure, it just means solve for this condition. So it's just another word that chemists use for heat of reaction or heat of vaporization or heat of fusion for a particular condition. Because it does change if you're at a different temperature.